After definition of the Newtonian Sobolev functions, we have been trying to look at very concrete examples and try to see what the N1P spaces look like on these. Please refer to the previous lectures on other examples. In this one, we look at a rather simple space, and I was pleasantly surprised that the N1P theory is already quite interesting on that. We're looking at the compact interval on R1 equipped with the usual metric, Euclidean metric, and the measure on that is the Lebesgue measure. So we have a metric measure space, and it's path connected, it's quite well connected. Let's try to see what the Newtonian Sobolev functions on this space look like. The first one we want to look at is the N11. So let's take P equal 1. So we're looking at N11 on this X. So I will not specify with notation the measure and the metric from now on. And the claim, the theorem, if we shall call it, that I want to prove is that N1P of X is nothing other than absolutely continuous functions on the interval 0, 1. In the beginning lectures, when we tried to motivate the development of Newtonian Sobolev functions, we actually started off by talking about absolute continuity and its connection to the fundamental theorem of calculus and stuff. So now that we have developed the theory in general, let's go back there and verify this claim. Okay, so let's see why, if you are in AC, then you are in the Sobolev class. So fix a function u in the space of absolutely continuous functions on 0, 1. Well, absolute continuity pretty much makes only sense on compact domains as we have defined it. Okay, by this Lebesgue's theorem, we know that there exists a not locally because it's compact, it just makes sense, an integrable function g tilde over the intervals 0, 1, which is indeed just the classical difference quotient derivative of u, but we don't care what it is exactly. We know that there is such an L1 function with the property that for every x and y that you pick in the interval, the fundamental theorem of calculus holds. And because I don't want to say which one of these are bigger, I put the absolute value, and then from x to y, this g tilde t dt. So we have this hold for this g tilde. To prove that u belongs to the Newtonian Sobolev functions, and we will not change its representative, by the way, because it's already a continuous function, as it's as nice as it could get. The exact representative that we have in hand will belong to N11. So we need to show that it has an upper gradient. Technically, upper gradients need to be Borel, which is the reason why we do the following adjustment. So let G, which is non-negative, be a Borel function that is almost everywhere, Lebesgue almost everywhere, equal to G tilde absolute value. So G tilde absolute value is a measurable function that does belong to L1. Actually, later when we talk about weak upper gradients, we will not even need to bother with this Borelness here. But for now, we need to verify that our upper gradient is actually a Borel function. But this G tilde is measurable. It's in L1. It's pretty much what we want. But since we need a Borel function, we can actually adjust it on a set of measure 0 to make it Borel. This is generally true that for every measurable function, you can find a Borel function that agrees with it almost everywhere. So the claim is, once we find this G, that G is an upper gradient of this U. Okay, so to prove this claim, obviously you want to take an arbitrary, so fix arbitrary rectifiable curve gamma in the space X, which is the interval 0, 1, and let X be gamma of 0, give it names, and Y be gamma of 1. They are 2 points in the closed interval. And let gamma xy be the obvious curve that joins X to Y. Because if you pick 2 points in the unit interval, there is one curve, the obvious one, that just connects the two, the line segment between them. But our arbitrary curve could go in many different ways from X to Y. So it travel and then go backward and then forward again and then come back. So it could have infinite, actually, back and forth until it settles there. So what happens here is you have the fact from above that U of gamma 0, which is just X, minus U of gamma 1, the end points, is Ux minus Uy, and that is less than or equal, because it was equal to integral of G tilde. Once you put the absolute value inside, then you get G of ds over this curve gamma xy, which is just the interval from X to Y. But then here comes a claim that I will not prove, but this is less than integrating G over the longer, let's say, curve gamma. There are 2 ways of doing this. Either you want to go and prove that there is a subpath, modulus some reparameterization and cutting and gluing of the domain of definition. There is a subpath of gamma which agrees with gamma xy, so that this inequality then holds because you're integrating over a part of a curve. Or the other one that I kind of like better is there is this equivalent definition from area formula that integrating a function along a curve is the same as, well, integrating over the image of the curve. Now we're doing kind of an intrinsic integration, and times the multiplicity function of gamma x, which counts how many times the curve hits the point x against the Hausdorff one-dimensional measure. Once you have this, then it becomes immediate that this is bigger than that, because you're talking about the image of gamma xy is a subset of this image, and the rest of the integrand is pretty much the same. Well, actually, the multiplicity in this case, n becomes just 1, and you have the same gx and dh1x. So this is another way to prove that inequality. Once you have that, then what we see here in the picture is that we started with an arbitrary curve, and we showed that the value of u at the 2 endpoints, when you look at their difference, is bounded by the curve integral of this g. Since gamma was arbitrary, so g is indeed an upper gradient. Okay, now observe that G is in L1 of the space X because G tilde was. Um, Also, because u is bounded from above and below, being a continuous function on a compact interval, u belongs to L1 of x as well. And this is all that is needed to show that a function is in N1 of x. So it's an L1 measurable function with an L1 measurable upper gradient. So that proves this direction. When you start with an AC function, then you end up in N11. For the backward direction, so now for the reverse, let u be in N11 of x. This means, so what do we know just from this inclusion? This means u is measurable. That's part of the definition of N11. U belongs to L1 of 0, 1. Okay, and there exists Borel non-negative upper gradient in L1 of 0, 1 such that G is an upper gradient. So from this, we get the following, that if x and y belong to, let's say, to the unit interval, and without loss of generality, say x is less than y, then the line, using the line segment as the curve, using this gamma xy that I identified above as the canonical straight line connecting them, using this, we have, well, what do we know? That u of x minus u of y, which is the values at the endpoints, is bounded by integrating over gamma xy this function upper gradient gs ds, and this is just go from x to y, integrate gt dt, because it's just an injective curve. And this is for every x and y, remember. Since G is in L1 of 0, 1, and we've seen this multiple times in different ways previously in the beginning lectures, again, when we talked extensively about AC and its connection to having some L1 derivative, basically. Since this is in L1, we see that U is AC. Yeah, so you have any union of disjoint intervals, say AI, BI, then you have this U of BI minus U AI. You take absolute value, you take sum over I. This should be familiar by now to you. And because the intervals were disjoint, so this becomes union of AI, BI, this function GT dt. But now if you make this measure very small, this will be arbitrarily small by absolute continuity of integral. If you have an L1 function, then by making the domain of integration, actually doesn't have to be union of intervals. If the measure of this becomes less than delta, you can make this less than epsilon. That was basically the proof. So starting with an N1 function, we ended up showing that U actually belongs to AC, um, which means that the class of n11 functions over X is sitting inside AC. And that ends the proof, completes the proof that AC and n11 are equal. So let me write this down and then let me double check something. N11 of X is none other than AC of 0, 1. So when we started with AC, already we know we have a continuous function. So we didn't have to worry about choosing representative. Coming backward, we start with the Sobolev function, and we have already seen examples that you can still alter a Newtonian Sobolev function on some small set and be equivalent to that exact same function. But here, because we're working in dimension 1, no point has zero capacity, basically. No point is forgivable. Therefore, we cannot actually change the representative of the function u. Based on this proof, you automatically see that u belonging to n11 voluntarily becomes continuous. So if you have been exposed to the literature before, to this notion of quasi-continuity, this says that u has no different representative that is quasi everywhere equal to it. And this is special, again, because we're looking at a very one-dimensional object. This says that you don't even have to alter the representative to be absolutely continuous. Okay, so that is very nice to see. So again, the importance of AC functions shows itself. As an exercise, then I can probably have you work on N1P. What will N1P of 0, 1 look like? How can you characterize that through, again, absolute continuity, but of course you need some other condition because N1P is not equal to N11. Okay, so with that, we have yet another concrete example of a metric measure space, and we have identified the N1P spaces. What spaces should we look next? You can also put that in comments. Probably trees are quite interesting, or finite graphs, let's say, because that's the next thing you do once you have for line segment. But we'll see. We're having fun, aren't we?